Okay, so to really understand how standard deviation relates to experimental uncertainty, we need to take a quick trip into the world of statistics. So what I'm showing here is a normal distribution. The reason that this distribution is important to us is because, remember, we spent a lot of time and effort taking a statistically meaningful number of identical measurements. What that means is that we did everything in our power to reduce and eliminate systematic error, so that the only error in our measurements that we can expect are random errors. And we can't do anything about random errors. Random errors happen every time you take a measurement, and they happen to follow a normal distribution. So that's essentially why this distribution is because it's representative of the random errors in our experimental process. Now, what I show here on the x-axis, this value 0 is the distance away from the average value that we calculated using that average value equation on the previous slide. So 0 distance from that value means that we're sitting right on that value. That means that this line corresponds to that calculated average value. And then as I move up in the x direction to 1 standard deviation, 2 standard deviations, and 3 standard deviations, those are all representative of experimental values that are that much larger than the average value. And then as I move down on the x-axis, -1, -2, -3 standard deviations, those are also representative of values that are smaller by that amount from this average value that I've calculated. That's the x-axis. On the y-axis, I've got the frequency. And as you would expect, because random errors are pretty small, most of our measured values are going to cluster around that average value. So here's the average value, and here is the peak of the curve associated with a very high frequency of values clustered around that average value. Now, how do we use this to determine the experimental uncertainty that we would ultimately report from our experimental measurement? Well, if we look at these blue shaded areas, from -1 standard deviation to the average value, it represents an area under this curve of 34.1%, and the same 34.1% from the average value up to 1 standard deviation above the average value, because this curve is symmetrical. So I'm going to combine these two areas, and what I end up with is 68.2%. That means that 68.2% of the area under this curve is contained between -1 and +1 standard deviation surrounding the average value. What this means from a practical standpoint is next time I take a measurement, there is an 68.2% chance that the measurement will fall between -1 and +1 standard deviations of this average value. So 68.2% is pretty good, but we are engineers and we like to be even more precise than that. And so instead of using 1 standard deviation, we use 2 standard deviations, meaning we're combining these slightly paler blue shaded areas, 13.6% below, 13.6% above, with the 34.1% and 34.1% we already have, to give us a combined area under the curve from -2 standard deviations to +2 standard deviations of 95.4%. So what this means is that the next time we take a measurement, there's a 95.4% chance that that measurement is going to fall between -2 and +2 standard deviations of the calculated average value. That's pretty good. 95.4%, that's good enough for engineering analysis. And so that's the value that we typically use, -2 to +2 standard deviations. And so when we report our experimental uncertainty, we will first report the average value as the value that we've measured, and then we will add to it brackets, a range of -2 to +2 standard deviations. And so you see here, 2 standard deviations is equal to S, where S is the uncertainty. And again, we have a 95.4% confidence that the next time we take a measurement, that value will fall somewhere within this range of uncertainty values from -2 to +2 standard deviations. And so that's called the confidence interval. So in engineering, we use a 95.4% confidence interval. Now, what happens if your uncertainty is even larger? Say you go up to 3 standard deviations above and 3 standard deviations below the average value. Well, all that does is take this even lighter shaded blue area, 2.1% under the curve and 2.1% under the curve on the positive side, and add that to your confidence interval. So it's okay if you want to report 3 standard deviations as your experimental uncertainty instead of 2, you will simply expand the confidence interval. And we'll see why that's important here in the next slide as we talk about how to report experimental uncertainty. All right, so the mechanics of reporting uncertainty follow a series of rules. So we typically report our experimental measurement with its uncertainty and the units. Units are very important in engineering in the following format. So the average value plus or minus the uncertainty and then the units. Now it's important that we do not report the units twice because this leads to confusion. So do not report the average value units plus or minus the uncertainty units. For example, when you report a temperature, you would not report 100 degrees Celsius plus or minus 1 degree Celsius. You would simply report 100 plus or minus 1 degree Celsius. Another aspect that causes some trouble in reporting is significant digits. A lot of times you have a average measured value and then you have an experimental uncertainty that you believe you know out to 15 or 20 significant digits, but it turns out that the number of significant digits are determined by the significant digits set by the x value, by the average value. So we report the experimental uncertainty to the same number of decimal places as we've truncated the experimental value, the average value, based on the number of significant digits used to develop that average value. So what this means, again, if we're measuring temperature, that we would not report an uncertainty of 100 plus or minus 1.6 degrees Celsius because the decimal place is right there after the 1 spot in this number 100, and by reporting 1.6 degrees Celsius as the uncertainty, we've all of a sudden added an extra significant digit, the tenths place, the decimal tenths place, that doesn't appear in the average value. So instead, we're going to round this value, truncate this value, so that the number of significant digits matches. And so instead of 100 plus or minus 1.6 degrees Celsius, we would report 100 plus or minus 2 degrees Celsius. Now, it looks like I've just done something very weird, right? I've just rounded this number up, and so I've therefore increased the confidence interval of this measurement that I've reported. Now, it's fine for me to do that because remember, from an engineering perspective, we're happy with a 95.4% confidence interval. And so if I've just rounded this uncertainty up, all I've done, if I go back a slide here, is to, instead of reporting the uncertainty here at 95.4% confidence interval, I've rounded up, and so I've reported it somewhere out here. I've just simply increased the confidence interval. And so it's always okay to round up experimental uncertainty values. It's not okay to round them down, because if you round them down, you're reducing the confidence interval below that 95.4%, which is accepted in reporting engineering values. Okay, so that leads us to the end of this fluid mechanics lecture on uncertainty analysis and experimental measurement following the statistical approach. I appreciate your time, and we'll see you at the next lecture. Thanks. Bye.